Alright, hello everyone, my name is Samuel Martinez Jr., and this is my video for Lab 1 Constant Velocity. The slides are divided into the following 5 sections: introduction, concepts, experiment, post-experiment, and then questions. The purpose of this lab is to use a real-world and a virtual experiment to display constant velocity while relating to physics principles, these being Newton's second law or the momentum principle. The two experiments will also later be compared against each other in a line graph. Here are the principles reiterated. This time we also have the velocity update formula. And a brief look at our results have the two lines diverging, which will be explained later on. So just to tie in how Newton's second law relates to the velocity update formula, Newton's second law equals the momentum principle. That brings about the momentum update formula, which brings about the velocity update formula. So velocity final equals velocity initial plus A delta t. A delta t comes from net force not being zero. When net force is zero, A delta t is zero, leaving velocity final to equal velocity initial. And for the sake of this lab, we are assuming that the only surrounding force will be my hand, that we are ignoring all other forces. Velocity is constant, equaling initial and final. The system is a toy car, the surrounding being my hand pushing the toy car, and the initial condition is that the car is already moving at time 0. The procedure for this experiment, real world, setting up a test site, pushing the car while recording, analyzing the video using the tracker application, and inputting that data into a table for comparison. Here is a screenshot of the tracker application after analyzing the video. The initial position starts at 0.03882 meters, and we get an average velocity of 1.3459 meters per second. This is taken from the whole length of the graph, from beginning position to end position. This data is then used for glow script for the virtual experiment later on. And note that we only took 0.2 seconds of data. So the steps for the virtual experiment: using the vector and the initial position from the real experiment, inputting that new data into code, running the code, and inputting that data into a table. So here we just have our code screenshots from GlowScript, the change being over here, where the vector for initial position and the velocity are changed. Those represent the values that we took from the tracker application for our real world. We're using those initial conditions for the virtual experiment. And some screenshots from that. The top left is just an image of what the ball would look like in that condition. The bottom left shows velocity is constant. The bottom right is a graph where position and time, that the velocity is constant, position is increasing. The top right is where our data is needed. The time only goes to 0.2 seconds, and then this Y column represents our X value distance. So taking the two data from tracker, real world, and GlowScript virtual, we end up getting these graphs that are a little janky, but putting them through Google's process allows us to get linear lines. However, the lines are different in slope and even in their intercept. Now, to explain why this occurs, why is the real world graph faster than the virtual graph? And a possible error here may be that when I took the average velocity, the car was already slowing down. Therefore, it was giving GlowScript a slower velocity to start off with. It was slow from the get-go. Some other errors that can be explained for this experiment are that the toy car moves along the z-axis, that there are still real-world forces acting on the car, and the GlowScript itself does have difficulties in its code data. It was also noticed that trying to update certain parts of the code end up causing entire magnitudes of difference in position. The only way to possibly remedy this is to have a longer distance, just so that tracker can analyze better. A better car or test site, reducing those surrounding forces, and then an analysis of the GlowScript code and multiple trials, just so that we can get a better average. As for end questions, what would happen if the axes were changed, these being the x-axis? Regardless of if the velocity were facing a negative or positive, it would just change the sign of the velocity, but it would still be moving in that direction. It would still be moving with that much force. The absolute value of a negative or positive velocity is still the same. As for setting net force to 0, it would just describe that velocity is constant, there are no other forces acting on the car. As for adding forces together to get net zero force, it's impossible. It's impossible to realistically achieve that or to even figure that one out, that there are just so many forces. And if there is a force acting on the car, it is going to be not net zero. So, thank you for watching.